The second course of lectures, motion plane in the Sub-Riemannian context. Very good.
Thank you very much. First, I would like to thank the organizer to invite me at this beautiful place. And so, first I want. So this will be an engineering series of lectures. Okay.
Not really.
I am not mathematician.
He is joking.
Before starting, I want to try to motivate a little bit what I want to do by certain examples. So let me start with the movie. This movie. It is a ball rolling on a plane, and as you can see, there is a cross at the top of the ball. And in fact, I did not draw it because I am not a very good drawer, but there is a cat sitting at the top of the ball, and at the end there is a mouse, and the cat wants to go in the direction of the mouse by remaining seated. So it means that let me continue. Let me do it again. It means that, so you see the cat is sitting here, looking in this direction, and he wants to go in this direction to the mouse, but he has to remain seated. And then what you want to do, in fact, with respect, is to approximate the motion that will appear just in a few seconds. This motion that comes now. The ball is rolling with full slipping, and you want to approximate this rolling with full slipping. You want to approximate it by rolling without slipping, and as you can see,
And twisting also.
without twisting also. Without twisting and without slipping. And sorry. And as you can see, you can do it. You can make the motion as close as possible to the full slipping motion. You can imagine that you just reduce the size of these loops. And you see that there are not so many solutions for a motion to approximate this motion. So let me show second examples. I have 3 examples to show you. Second example is this one. It is a ball which is pulling a trailer. And this ball, you would like it to move together with the trailer in this direction, completely, transversally. Then you would like to approximate not only rolling without slipping rolling with full slipping by rolling without, but also you want the trailer to move transversally to to this direction. You see, you start in this direction and you go. You want to go to move in this way, and you want the trailer to move also transversally, like that. Then this is a solution. And to finish, my last example is the very interesting following problem, parking problem. You have two walls, 10 meters, 10 meters, 1 centimeter. This large, and you have a car with 5 trailers, 1, 2, 3, with 4 trailers. Here is the car, here are the trailers. And the total length of these guys is 10 meters, and you want to park here. Okay, it is perfectly possible.
It's impossible.
It is possible, completely clearly. And I will show you. So there are a lot of standards. This problem was studied by a lot of people. Hector Sussman and some of his students, some guys from robotics that are well known, Jean-Paul Lomont and others. Hector Sussman, who is a guy named Laferrière. You can find 100 publications on this subject. It is a very interesting subject. Moreover, so there are solutions. What I claim is that I do it in optimal way. More with respect to what the other guys did, I do it in optimal way. What does it mean in that case, optimal way? Optimal way means once you fix the velocity of the pulling car to 1, the time to park up to epsilon, up to some epsilon, the time to park is as small as possible. Time for parking is minimum, up to epsilon. And so I have a methodology to do that. And there are standard solutions, the solutions of this guy. Then to finish, I made a race. I have the movie of a race between the standard solution and my solution. Here it is. So on the left is my solution, on the right is the standard solution. I already arrived up to the specified epsilon. I am the best. Okay. So these are just 3 examples of the general problem I want to treat, and this general question in kinematic robotics. You have a kinematic object. For this kinematic object, you have trajectories. For instance, the trajectory of the ball that is supposed to roll without slipping, and you have non-admissible trajectory, slipping, and okay, and so it is a question of for non-holonomic systems to approximate non-admissible trajectories by admissible ones. So I shall try to formalize the problem. To formalize the problem, I need to. My general context is the context of Sub-Riemannian geometry. So, do I need to recall what is a Sub-Riemannian? Is it necessary that I recall what a Sub-Riemannian metric is or not? I don't know. the audience. Should I?
Better to do. There are some people who.
Better to do? Okay. So, what is a Sub-Riemannian metric? Sub-Riemannian structure, if you want. You are given a manifold M, and you are given a distribution, a vector distribution, delta, of, so M has the dimension n, and delta has rank k, rank delta equals k, and then the corank of delta, corank of delta is n minus k equals p. Okay, and so this distribution, you assume it to be complete. Delta is assumed to be completely non-integrable. Everything is smooth, and sufficient condition for this is that if you consider delta plus delta bracket delta, which means plus, and you continue like that, delta bracket delta, and so on. You consider this guy, and this guy is equal to the full tangent space. Maybe this is not enough, I don't know. Do I get all brackets like that?
Yes.
Yes. So this should be equal just to the tangent boundary. It is a Hormander condition, a controllability condition, and so on. And so I assume this, and I am also given. So I am given delta, and I am given G, and what is G? G is a Riemannian metric over delta. Metric over delta. Which means that I can measure the length. I can measure the length of tangent vectors to a curve, provided that these tangent vectors are in delta. But admissible curve is a curve which is absolutely continuous and almost everywhere tangent to delta. And then for such a curve, I can measure the length of the curve via the Riemannian metric. Okay. Then this is and in fact it turned out that due to the non-integrability condition, this gives to M the structure of a metric space, because due to the non-integrability condition, given 2 points, x0, x1, you can find an admissible curve that connects x0 to x1, and then you have the length of this admissible curve, length of gamma, and what is the distance from x0 to x1? It is the minimum of the length over all possible admissible curves connecting x0 to x1. Okay. So the difference with Riemannian geometry is the fact that you restrict the family of admissible curve. They have to be tangent to some non-integrable distribution. I go to, for instance, okay, then this is a Sub-Riemannian metric. I can explain you how to connect this concept to the examples that I just presented. So, for instance, for the ball, or the ball rolling on the plane that I presented here, what are the equations? So the equations are like that. Omega, where omega is a skew-symmetric matrix, U1, U2, 0, minus U1, minus U2, and x dot equals U. X is x1, x2, and U is U1, U2. Okay. So, and so R belongs to SO3, of course. So this is R is the frame attached to the ball, orthonormal frame attached to the ball. Omega is skew-symmetric matrix. U1, U2 are the controls. It means that when U1, U2 are the controls, they are just derivatives. The derivatives of the motion of the contact point of the ball to the plane. You know, the point X is moving on the plane with velocity vector U, that I will consider the control variable, and the only thing that you can choose, if you assume that you are rolling without slipping and twisting, is once you choose U of t, it completely determines the motion completely. You just have to, if you are at a point, you just have to choose the direction on the plane along which you want that the contact point moves. So so Rx belong to SO3 times R2, which is the state space. And you can rewrite it, so you can rewrite the equations in control form. So like that, x1 of q. So R is the state, so it would be q dot equals x1 of q u1 plus x2 of q u2. You just rewrite these equations like that, and you see that in this manifold, which is a group, by the way, and in fact the system is left invariant with respect to some semi-direct product group structure, but this is of no importance in my case, because almost all the kinematic systems that I consider are they are academic kinematic systems. They are more or less all moving on certain Lie groups. But the fact that I want, this is absolutely of no importance in my theory, because after that I want to follow a certain curve, the curve to be approximated by the motion of the system, and the choice of this curve kills completely the left invariant structure. Then left invariant structure is of of no importance at all in all of these examples. And I am like that. So what is the distribution delta? The distribution delta is just a distribution generated by the two vector fields x1, x2. So delta is the span of the vector fields x1, x2. It is this distribution. And it is quite natural to, and I choose and now I have also a natural Sub-Riemannian metric, that is a natural metric on the distribution. Okay, it corresponds just to choosing the, saying that x1, x2 forms orthonormal frame for the metric. Which means, okay, so in this example, so I am given a Sub-Riemannian metric. The Sub-Riemannian metric is completely specified in this control way of writing the things. This is a control system with controls U1, U2. Okay, and so it defines at the same time the distribution, which is a span, which is the vector space generated by the vector field x1, x2, and it defines a metric by the fact that I require that x1, x2 are orthonormal frame for the metric. Then this is the ball, and okay, the trajectory that I want to approximate is a certain curve in SO3 times R2, and what curve was it in that case? It was a curve which is R of t. It remains the identity matrix. You don't want the frame to move, and you want x of t to be 0t. You want to move along the vertical frame. Then you want to approximate this curve, gamma of t, which is clearly non-admissible. It is slipping. Problem?
What does it mean sleeping?
Yes.
What does it mean sleeping?
Slipping. Slip.
Ah, sleep.
You want the frame to be fixed, and the contact point, you are sleeping. Okay, so this was the first the first example that I presented. Here are the equations. Here is the curve to be approximated. Now I say approximated, but approximating in which sense? There is a very natural fact. We have a metric. Our general space is a metric space. We have we have the full space, the configuration space of the system. We have a non-admissible curve gamma to be approximated, and we have a metric. Then the first way to do the thing is to approximate the motion uniformly C0 up to epsilon with respect to this metric. That is to consider the tube around this non-admissible curve gamma, the tube of radius epsilon. By the way, it is not clear at all that this tube is something smooth up to now. Okay. Then you are. Then the data is the Sub-Riemannian metric given under this form of a control system. But it is the Sub-Riemannian metric and the non-admissible curve. And what I want to do is to approximate this non-admissible curve by admissible 1 up to epsilon in up to epsilon. This epsilon is the Sub-Riemannian epsilon, the epsilon of the Sub-Riemannian distance. This is my problem. Okay? So now it is a very general problem. I have Sub-Riemannian metric and non-admissible curve. Of course, if the curve is admissible, it is not very difficult to approximate by admissible. Then the problem is very easy. Then just you have the data of a Sub-Riemannian metric and a non-admissible curve, and you want to approximate up to epsilon. Since you are engineers, you want, if possible, to do it in a constructive way, which means that for any epsilon small, for all epsilon small, and given, and you want to construct an admissible curve, gamma epsilon, okay, which approximates up to epsilon the given non-admissible curve gamma. That is, you are looking, a constructive solution is just exhibiting a one-parameter family of curve, of admissible curve, in such a way that for all epsilon, you remain in the tube of radius epsilon around the. It is also. Okay. Of course, what is clear, so what about the length, the Sub-Riemannian length? This curve gamma epsilon is admissible. Then I can measure its length. What about the length of the curve gamma epsilon? What about the limit when epsilon goes to 0 or the length of this curve? What do you think of that? It must go to infinity. Of course. Then, in fact, it turned out that, and it will be, I will go. So, I shall not be very precise for the moment. It is just introduction. So, let me. In many cases, it will be like that. This L of gamma epsilon, the best, will be of the following form: 1 over epsilon p, 1 over epsilon p times a certain function phi of epsilon, which is smooth. Okay. And then, so this function phi of epsilon is smooth, and so the asymptotics of this function phi, the leading term when epsilon tends to 0, is something important in the problem. It gives you the up to this 1 over epsilon p, it gives you a measure of the length of your it is a certain measure of the length of your non-admissible path. It is what I would like to do. Then, in fact, this work started more than 15 years ago, and Andrea Grachov asked me to. So now it is almost finished. I will, but Andrea Grachov asked me to talk about the full story from the very beginning. then please, in fact, I realized when I prepared this lecture that the first things from 15 years ago I don't remember. Then I will probably say things that are wrong. You will correct me, but I really don't remember the beginning of the story. And it is not so easy. So most of this work, I have to say last word, most of this work was done in collaboration with Volodya Zakaliukin, that maybe some of you knew. And unfortunately he died 3 years ago now. And I dedicate, of course, this series of lectures to him. I gave to the organizers of the conference more or less reorganized series of papers that talk about the story from the beginning to now. The paper about this parking problem just appeared 2 months ago, so it started 15 years ago, but it is not yet finished. But it is almost finished. It is almost finished, at least in one case. In the case where the rank k of the distribution is equal to 2 controls. Of course, I have a lot of results that I will talk about in the other cases, but the case k equals 2 is especially interesting. All the examples I gave are of this type. They are all, and to finish, to introduce and to motivate what I will do, I want to comment, but very roughly, not precisely, where I want to go in that case. Of course, I will not treat only that case, but this is the very interesting case. So, as you will see, k equals 2, which means that the system is x dot equals x1 u1 plus x2 u2. You are on a manifold, and x1, x2 are 2 vector fields that are orthonormal bases, that are orthonormal frame for the metric. And in that case, there are certain, I have the curve gamma, which is given here. Gamma is a curve, so it is a map. And it is a smooth curve. It is a smooth non-admissible that I want to approximate up to epsilon. Then this is the data. It is my motion planning problem. Okay? Then there are some very special coordinates in that case that I call normal coordinates. Normal coordinates. And this choice is really in accordance with the word normal is in accordance with normal coordinates of Riemannian geometry. It is exactly like that. And you have normal coordinates, and these normal coordinates, they are shared in 2 pieces. First part and second part, x, y, and in fact, x, you can consider that these coordinates as coordinates in the distribution, in delta. It means that it means that along the curve gamma, along gamma, it means that at gamma of t, the distribution delta gamma of t is just ddx1, ddx2. Okay? These are normal coordinates are like that. The distribution is two-dimensional when it is like that. Then the result where I want to go, so there are these normal coordinates that I will make precise in the second part today of my lecture. Okay. So situation is like that. You have these normal coordinates that I shall define in later. And to the distribution delta is attached a certain flag, natural flag of distribution. There are several, by the way, but the flag I will consider is the following. You have the first distribution, delta 0 is just delta. The delta 1 is delta plus delta delta, and so on. You continue like that. Delta 2 is delta 1 plus delta delta 1, and so on. So you consider this flag of distributions, okay? Then delta 0 is contained in delta 1 to delta p, which is equal to the tangent plane, to the tangent bundle, due to my non-integrability assumption. Due to the non-integrability assumption, you have these inclusions. This is the non-integrability assumption. And then you have numbers. This number is the dimension of the distribution. The following number is the dimension of delta 1, must be 3, or maybe 2 at some points, but 3 at least at generic points. For delta 2, there are this dimension of delta 2, there are two possibilities in that case. It can be 4 or 5. By the way, if you consider the kinematic system of the car with pulling a single trailer, then the numbers are 2, 3, 4. And if you consider the ball rolling on a plane, the numbers are 2, 3, 5. Okay? It is like that now. Etc. Okay? You have this series of series of numbers, and then so here you have brackets of order 0, brackets of order 1, brackets of order 2, brackets of order 3, and so on, and you reach the tangent plane for brackets of order p. You reach the tangent plane for brackets of order p. And the results are as follows. Well, what we feel. Then, you consider the optimal trajectory. The optimal trajectories are optimal trajectories up to epsilon. They depend on epsilon, but I renormalize. There is some natural way to renormalize with respect to this epsilon. And if p equals 1, optimal trajectory, if I project on the coordinates in delta. Optimal trajectories are like circles. Okay. So this is the case for the single kinematic car, known under the name of Dubin's car. Equations are very simple. I can rewrite here Dubin's car. It is a car, just a car. So you have x dot equals cosine theta u1, y dot equals sine theta u2, theta dot, u1, and theta dot equals u2. If you want to turn, you apply u2. If you want to go straight on in the direction of the car, you apply u1. It is very simple. Yes. This is a Dubin's car. Then in P equals 1, you have this. P equals 2. P equals 2 is the car, I shall say more about that, is the car pulling a trailer. And optimal trajectories projected in horizontally in normal coordinates are like that. It is this curve is I don't know if you know about elastic curves. It is elastic curves are, you consider an elastic rod with a constant what? What is the name?
Euler.
Constant elasticity. It is elastic rod with constant elasticity. Okay, homogeneous elasticity, and you consider all the possible equilibrium positions of these elastic rods with homogeneous elasticity. Okay, then you have several, but there is a single one which is periodic. It is this one.
Also the circle. Circle is also.
Circle also. Circle is special. There is the circle.
Except on circle, there is only one.
Yeah, circle is the first. Okay, I agree. Non-trigonometric one. So they are in fact elliptic curves, and the only two periodic ones are the circle and this one. And the case 2, 3, 5, 6. So this is the case of the ball rolling on the plane. Okay? If you remember the motion of the ball rolling on the plane on my movie, curves were like that. They were not. The motion, if you project in a different direction, if you project in the convenient way to normal coordinates, it gives you this picture. Then after, with Volodia, we came to the ball pulling a trailer, so which is a third bracket. What we got as solutions of this problem asymptotically and renormalized is a certain also periodic hyperelliptic curve which is like that. If you remember my ball pulling a trailer, you could see some deformations of this motion, and then there is a quite clear conjecture at this point. First bracket, you have the circle. Second bracket, you have this elastic curve with two loops. Third bracket, you have this three-loop hyperelliptic curve. Then conjecture is clear. But what? So this is more or less the end of the story in the two control cases. Very recently, I proved that for the Gursa case. What is the Gursa distribution? A Gursa distribution is a distribution such that the flag increases by 1, always increases by 1. Then it is 2, 3, 4, 5, etc. Then the conjecture holds true for Gursa distributions. This is my very recent result. If the distribution is Gursa, then the figure is in normal coordinates, the figure of asymptotically optimal curve is a certain n loops, is a certain, p loops, hyperelliptic curve. It is a p loops, hyperelliptic curve. The number of loops is the number of brackets you need. Number of loops is the number of brackets you need. It is a hyperelliptic curve. It doesn't look, but it's just my jet lag. But at the same time, I understood that in non-Gursa case, this is certainly not true. And the fact that everything is true up to the third bracket is something exceptional. But after third bracket, no chance that it continues to be true in general. What is remarkable is that it continues to be true in Gursa case, and what is very interesting is that the Gursa case is the case of my race movie, parking race movie. It is the case of a car pulling an arbitrary number of trailers. Each time you add a trailer, you add a bracket. It is like that kinematically. You add a trailer, you add a bracket. Then car with any number of trailer corresponds to Gursa structure. And then for the car pulling a trailer, the conjecture holds true. There is no chance that it holds true starting from p equals 4. I understood why very clearly now. So I think that I am just